Thank you for being here this evening. My name's Reed Corbett. I'm the Executive Director here at the Coastal Studies Institute. We're excited to provide one of our many Science on the Sounds this evening, but I wanted to give you a couple of announcements. I always like to start the welcome with announcements for something. Maybe it was something with middle school and doing the announcements there. And so we are always excited to sort of bring the community into CSI. So again, I appreciate y'all coming this evening and those that are online watching. But we have another opportunity for you to come and spend some time with CSI this weekend. We have our open house this weekend, our annual open house. This one is a bit bigger. We're excited. It's 10 years that we've been on this campus. As of January, it's been 10 years on this campus. And so we're bringing some other partners to campus, including the Coastal Fed, College of the Albemarle, Jeanette's Pier, and many other of our partners here on campus as part of Earth Day. And so I hope you can make it. Tell your neighbors, tell your friends. We really look forward to having a great event again. We do tend to bring somewhere between 300 and 500 people, and we hope we can break our previous records. So it's this Saturday, Earth Day, from 11 to 3. There is going to be at least a food truck here, so you can plan on having lunch here as well if you'd like. So we usually have a hiatus of Science on the Sounds during the summer, but we do have two more planned, one for May 18th, and one in June 15th. The one coming up May 18th is a group, it's a nonprofit group called Vesta that's working on potentially doing some work related to carbon capture off of the Duck Coast. And so it's an interesting project that may or may not move forward. They're working on permitting at this stage, but it's a really interesting project moving forward that's focused on carbon dioxide in the atmosphere as that relates to the ocean and actually trying to capture carbon. And so that'll be May 18th coming up. I'll encourage everybody, if you haven't already, there's a sign-up form. This is asking for your name and potential email to sign up for our newsletter. We're not going to blast you with emails every week, but we put out 3 newsletters a year, sort of highlighting our research, highlighting our students and the activities going on at the Coastal Studies Institute. So we encourage you to sign up for that as well. Many of you may be aware that East Carolina University just went through its annual fundraiser called Pirate Nation Gives. We were thrilled that we were able to, within our organization, raise just over $40,000 this year to support a lot of what we're doing for our students. A lot of that does go to scholarships. I'll encourage you to grab one of these handouts, which is focused on our mission and what we're trying to raise funds for, I guess. And we are always happy to chat about what you might like to donate to help support the Coastal Studies Institute moving forward. So I don't know if you want to clap on. Anyway, and so I want to introduce one of our own faculty here, Dr. Mike Mulia, who is our physical oceanographer here, who will invite our speaker.
Thank you, Reed, and welcome everybody. It's with great pleasure that I get to introduce my friend and colleague, Dr. Al Plueddemann, who is also a physical oceanographer. Al has his BS degree in engineering from the University of Michigan and master's and PhDs from Scripps Institute of Oceanography. He is currently a senior scientist at Woods Hole Oceanographic Institute in the Department of Physical Oceanography. His research is focused on upper ocean processes, including the fluxes of momentum and heat at the air-sea interface, and the structure of the ocean surface boundary layer and the response of the upper ocean to surface forcing. Something that I enjoyed reading about Al is that he is a seagoing observationalist like myself, which I appreciate, and he's an active participant in the ocean research community. So welcome, Al. Thank you for coming.
Thank you. Thanks, Mike and Reed for hosting me. Thank you all for coming here. And for those of you online, I want to assure you that the view for the people here is much better than your view back there. This is a really nice facility. I was really impressed to see it for the first time today. So let's get right into it. I'm going to talk to you about the relocation of the OOI Pioneer Ray. What's that all about? The Pioneer Ray is the name that we use for a collection of oceanographic tools that we put together in a collection in a certain kind of spacing and used in a certain way to address oceanographic questions. And I'll tell you what some of those questions are and show you how we're arranging the array. The OOI is the Ocean Observatories Initiative. It's, to my knowledge, the largest ocean observing, or sustained ocean observing research program in the US, and it's funded by the National Science Foundation, NSF. And that Pioneer Array, which was previously located south of Martha's Vineyard on what we call the New England Shelf, is being relocated. And it's going to be relocated right out there, right off of Nag's Head. Is it the wrong way? Right out there. See, you can see I've never been here before. That's, I see water that way, that's all. It's going to be relocated to the Southern Middle Atlantic Bight, or MAB, and we have taken to call this the MAB Pioneer Array. It's kind of ironic because the MAB is very large, and it goes from Cape Hatteras all the way up to Georges Bank, so that the old Pioneer Array on the New England Shelf was also in the MAB, but, you know, details. So let's get right into it. I want to give you a little bit of context first. This OOI, or Ocean Observatories Initiative, is comprised of lots of elements. It's a distributed, interdisciplinary, sustained ocean observatory. And the dots you see on the map are all the different locations where infrastructure and ocean observing elements either are or have been deployed. The two in the southern hemisphere there have been decommissioned, I guess you'd say, or discontinued due to some funding constraints, but the data from those are still available, and the other 5 sites are still operational. So you'll see here the Coastal Pioneer Array, but this is just one of these elements, right? So what I'm talking to you about is one piece of this larger system. So the Pioneer Array relocation. The Pioneer Array was actually developed and conceived, and it was a long time ago. I was trying to remember, I think it was 2004. I was working with some colleagues at Woods Hole, and we came up with the idea for a relocatable array that would be suitable for coastal observations. And when we say coastal, we didn't mean, you know, really in knee-deep water. We meant on the continental shelf, so a few hundred meters deep or so, and out to the upper continental slope where the bathymetry starts to drop off, and maybe up to 500 to 1,000 meters deep. So it's been deployed on the continental shelf and slope off the coast of New England from 2016 to 2022. And you can see in here, you probably can't see all the details, but this is a cartoon, basically, of the New England Shelf Pioneer Array. And those are depictions of all the different tools and bits and pieces that we're going to use for this MAB array off of Nag's Head. And I'll show you some of them, but not all of them, in some more detail later. So the key here is we don't have new funding to relocate this array, so the key is to utilize the equipment we already have. So we've recovered it from its location on the New England Shelf. It's being refurbished, retooled in certain ways. It's going to be redeployed in a slightly different configuration down here in the MAB. Before we leave the New England Shelf, though, it's really interesting to think about what we've learned there. It was deployed, you saw, for 6 or 7 years, depending where you count the start from. And it was actually very successful. I'm just showing a few of the peer-reviewed publications here that tell an interesting story. I won't go through them all in detail, but the high-level picture is that this was conceived by some of my colleagues, and I was part of that group to some extent, to be an array that would look for the small leakage between the continental slope and the continental shelf, the leakage of water and water properties, nutrients, salt, heat, back and forth from what we call the slope sea, which is off in the deep water, to the continental shelf. That process was envisioned to be slow and weak, and we thought we would have to make very sophisticated observations over a long period of time to find a signal, sort of the needle in the haystack. It turned out we were very wrong about how it worked, and that was absolutely fascinating because the phenomena that we saw were not the ones we expected. And so the list of things you see here are almost all unexpected results that were found from the New England Shelf Array. And so I'm hoping that we are going to have a similar experience here where we go into it with some hypotheses, some concepts, we think we know how the process works, and we're probably going to find things that are very different than what we expected. So this process of relocation is a pretty formal process. It's managed by the National Science Foundation, and it takes a long time, both because of technical issues of changing things around and because of bureaucratic and administrative issues. So NSF announced their intent to relocate in February 2020 at a national meeting, a national science meeting called the Ocean Sciences Meeting. They then convened, with our help, 2 different community workshops. They were called Innovations Labs, which is just a fancy name for a workshop. And they brought 20, 30, 40 community members together twice to discuss the potential to relocate this array. If so, where? If you decide where, then how? And we talked about it for a long time, over multiple days for these 2 different workshops. The ultimate decision was to relocate to the southern MAB, which I described. That was announced publicly in April 2021. And then we kind of turned a little bit inward. We took all that information that we had gleaned, and I'll give you a little sense of it in the next slide, from that Innovations Lab, and our job as the array operators was to make that happen. And we didn't have new funding for that, as I said, so the way to make it happen was to pull out the equipment we had in the water and not try to redeploy it on the New England shelf, take a little break and use some of the funding we weren't spending on that to fund the activities that needed to be done for the relocation. So here's a sense of what was coming out of that workshop. We developed a set of science themes, which I'll tell you about in maybe 1 or 2 slides from now. But this slide with the figure here talks a little bit about what we call the consensus array design. So if you can recognize some of the bathymetry and geometry here, there's Norfolk, for example, there's Cape Hatteras. So the participants in the workshop were asked what kind of science they wanted to do, and if they could describe that science, where would they do it? What would kind of the aerial region be? And some of them drew boxes, some of them had dots, some drew lines, and some were physical measurements, some were biogeochemical measurements. And one of my colleagues went home the night after that first day of the workshop and put all the dots and circles and squares and lines on the same map, and that's the map that came out. So our job was to take that and decide that we were going to come up with a coherent-looking, measurement array out of it. So that was our attempt to implement the consensus design. To do that, we had to use our existing inventory. As I said, we didn't have much new funding to buy new stuff. We had to make sure that it was feasible to operate. We had some really good ideas to put different kinds of equipment out that would have, for example, would not have fit on the ship. So that was a problem for us. We didn't have enough money to take out a second ship to do it. And there I just said it, operate within the existing budget, right, is the other constraint. So it takes a long time to do this. The complexity is, as I said, technical, administrative, and otherwise. We started in July 2021, and we've gone through the planning phase into an engineering phase, and that was focused to a large extent on coming up with mooring designs and then doing computer models to test those designs in the environment that we expected them to be in and the water depth that we expected them to be in, and see if they would survive and function the way we thought they would. And starting just a few months ago, around January of this year, we're in the implementation phase where we're now actually trying to get ready to put this equipment in the water. So you see there the 2 arrows in black showing that that New England Shelf Pioneer Array ended. Oh, I'm not pressing the pointer, that's why. The New England Shelf Pioneer Array ended in the fall of 2022 here, and we don't go back in the water for the MAB Pioneer until about a year from now. So what about this region? It's really interesting. It was fascinating to the workshop participants. It's very complex. And I tried to come up with 3 words that would just fit on this slide without wrapping around to the next line. That was my challenge. So I decided that the way to talk about this was convergence, Gulf Stream, and exchange. So this is a map that we got from we borrowed from the so-called Peach project. And I don't remember the exact acronym, but that was a science process study where I think the H anyway stands for Hatteras. So it was done here locally. And this is a cartoon that they used, but it shows some really interesting things. This is relatively cold water coming down, relative to the water in the south, coming down from the north. This water, like this MAB shelf and shelf break jet, can be traced all the way back up past New England, up to Georges Bank, and in some cases all the way up to the Labrador Sea. So this water is coming from a long ways away, but it can't get past Cape Hatteras because of this Gulf Stream here and the presence of southern MAB shelf water, which meet nominally at this Hatteras front. So there's a lot going on here. These water masses are all converging right at Cape Hatteras, right? They don't have anywhere to go except offshore, which results in a lot of exchange between the continental shelf and the continental slope further offshore. The Gulf Stream is an ever-present phenomenon. We did not want to be in it. So the operational constraints would be away from the Gulf Stream, and we also couldn't operate our infrastructure. I said we had to use what we had, right? We couldn't start all over with new equipment. We didn't believe we could operate in water depths shallower than about 30 meters. So we couldn't go too far west, we couldn't go too far south, and we actually couldn't operate in water deeper than about 600 meters. So the idea was that we had when you think about all those constraints, you end up with a box that's about like this red box here. It's about 60 by 60 kilometers or 30 by 30 miles in size. It's a box that you could put all those elements in and still have what you might call a coherent array, a spatially coherent array, which means what you measure at one location would be related to what you're measuring at another location. If you spread them out too far, if you made that box too big, they won't be coherent anymore, and you won't have an array. You'll just have a set of different measurements. So that's where we ended up. Decision to concentrate on the shelf slope region from about 30 to 600 meters depth. That's the east-west extent of this box. South of Chesapeake, we didn't want to really do an estuarine or coastal study. We wanted to do a shelf slope study. So we wanted to be relatively far from the Chesapeake, north of Cape Hatteras to stay away from the Gulf Stream. So there is a desire to extend further offshore and further to the north, and that we're not going to try to do that with moorings. We may be able to do that with these ocean gliders that I'll talk about. So that's where we ended up. What does the community want to do there? The science themes, there were a lot of these science issues and concepts brought up at the workshops. I think I counted 120 of these ideas or concepts or science questions. Those were condensed into a little more of a consensus at the workshop itself, and we got down to a smaller number that we then, in the program, condensed even further down to 3 overarching themes. And these are the themes here. So it's really about the dynamics of shelf-slope exchange, right? I've been talking about that for a while now. That is controlled primarily by things like wind forcing, instabilities, wiggliness of this front that I talked about, and the Gulf Stream influence, which also wiggles back and forth. This acronym here is biogeochemical. So a lot of the workshop participants were interested in multidisciplinary, not just the physics of the area, which I'm talking about there in the first bullet, but the biology and chemistry of the environment, and how things like carbon, nutrients, and particulates are transferred back and forth or vertically in the water column. And then as those things get transported and recycled, how does the ecosystem respond to that biogeochemical cycling? What we kept hearing over and over after we decided to go to the southern MAB was that we weren't going to be here very long before we got some extreme events like hurricanes. So we tried to model that in our mooring computer models to see if the moorings would survive, and we think they will. But doing it on a computer is going to be different than having it happen in real life. So we'll be very anxious when the first hurricane comes by. I said we had a toolkit, right? A set of gear that we use to make these observations, and you see the fundamental part of that toolkit here. Starting on the far right, what we call this coastal surface mooring. This is where I introduce a bunch of acronyms to you. So there'll be a test at the end for the 5 key acronyms. One of them is CSM, coastal surface mooring. That's the equipment on the right. You see it's comprised of a big buoy. I'll show you a picture of it in a minute. At the top, there's this thing called an NSIF. That's a near-surface instrument frame. That's where we put a lot of our equipment. It's a big cylindrical open structure that we can put clamps in and clamp a lot of instruments in. And then using these different types of mechanical and electromechanical devices, they're not devices, they are like wire, but it's more sophisticated than wire. We connect that surface frame down to the bottom to a thing called an MFN, a multifunction node. It's basically an anchor frame, a sophisticated anchor frame that holds the mooring in place. So this mooring has, I'll tell you a little bit more about it. It generates power at the surface, has instrumentation here and instrumentation at the bottom. In the middle is this electromechanical connector that has no instruments on it, right? Even in the cartoon, there's no instruments. So a good way to use this mooring is to put it next to a different style of mooring that has buoyancy at the bottom, buoyancy at the top from a sphere or subsurface, and then a buoy at the top. And that top and bottom buoyancy is enough to hold a simple wire, in this case, just like a 1/4 inch or 3/8 inch wire, very taut. It's very nearly straight up and down. And this device here, another acronym, WFP, Wire Fouling Profiler. That device is filled with instruments and batteries and a little motor and a wheel and a spring. And the spring pushes the wheel against the wire, the motor turns the wheel, and the device crawls up the wire, and then it can crawl back down the wire as well. So this so it follows the wire, right? Wire fouling profiler. It fills in the missing piece here between the NSIF and the MFN. So these two working together are a really nice pair. And you can already see why we need more than one tool to make these measurements. Those two things work together well. We try to put them at the same location within a few hundred meters of each other. They give you good information about how things change in time, but they're pretty far away, right? We have different sites that might be 10 miles away, something like that, right? So they're not telling you a lot about what's changing in space, how the space is how properties are varying in space between those two locations. You can get that information using different kinds of tools, things that fly through the water in some way or another. This one in the picture in the lower part here is called an ocean glider or a buoyancy-driven glider. It has the ability internally to change its internal buoyancy or how much flotation it has. So it will actually start to move up and down in the water column based on the change in this buoyancy internally. And if you put some wings on it and a rudder and get very clever about designs and how you can move weight around inside the vehicle as it goes up and down, you can actually make it fly, right? So starts to go down by changing its buoyancy. Because it has wings, it also moves forward. And if you shift some weight around inside and turn the rudder, you can make it actually turn. And so you can fly these gliders underwater, and what we use them to do is move up and down over and over and over again as they're moving forward. And they can basically paint a picture. Imagine this glider going along this wall and taking photographs, and maybe there's a mural on the wall that you want to know what it looks like. If you have a mooring, you know what the mural looks like over here in a lot of detail, and you know what it looks like way over there in a lot of detail, but you don't understand in between. You have these gliders go up and down, back over and over again between here and there, you can get a pretty good idea of what that picture looks like. Gliders are really nice. They're relatively robust, and they stay out in the water for a long time, 70 to 90 days, which is pretty good endurance for some tool like this. The drawback they have is they're really slow. They only go about 25 centimeters a second, or half a knot. So imagine, I'm asking Mike to take his boat out and do some work for us, but he can only go half a knot. It's like, he's gonna be like, Al, I don't have a week to get there. I gotta get there in a day. So these are really good for large scale things that you can take a long time to measure, but they're not fast enough to take a snapshot before the ocean changes. So if we go back to our mural on the wall analogy, imagine that the mural is not the same. If you come in tomorrow, it's a different picture. So if it takes you a week to go back and forth and paint that picture, or visualize that picture, you're not gonna really understand what it looks like. You've gotta go fast. You've gotta go faster before the picture changes. To do that, we use these propeller-driven vehicles. We call them AUVs, autonomous underwater vehicles. They go about 6 times as fast as these gliders. So you can paint the picture quickly, get the snapshot, and understand what's happening. Of course, they have a drawback too. They have very low endurance. You can only get about 24 hours of operation out of these before the batteries are depleted, because unlike the glider that's sedately moving up and down, this thing is spinning its propeller really fast to go at its 3-knot speed. So I hope that with this slide, I'm giving you a sense of why we need multiple tools. And we use these multiple tools in different ways that are best suited to what their capabilities are. And to make an array that can paint the whole picture of the ocean successfully, you need all these tools at once. That's kind of the concept that we use when we say an array. We have not just a sensor, but we have a whole array of information. So I thought I would dig a little bit into here. I think I'm going too slow in my talk. I don't want to spend too much time on this, but we'll just rip through 3 things here. I want to show you the buoy, the near surface frame, and the MFN, the anchor frame. So the buoy, here's a photograph of it. You can see it has instrumentation on top. You can probably tell that there's solar panels there on that fin. And if you have really good eyes, you can see right in here that there's some propeller blades. It actually has a wind turbine that generates power. So we generate power from solar panels and wind, recharge batteries that are in the middle part here. It's floated by a foam surrounding and generates power, and it is connected with these electromechanical elements down to the seafloor, to the NSIF, and all the way down to the MFN. So we get power and data back and forth from the sea surface to the seafloor. It's basically it's like a self-contained, computerized observational system all on its own. That middle piece, or the piece that's up at about 7 meters depth, is this near-surface instrument frame. The photo here gives you a sense of scale, how it is. It would stand about chest high on me. And you see from the picture looking down from above, just chock full of electronics, canisters, connectors, instrumentation, batteries, all kinds of other stuff. And at the bottom, we have this multifunction node, or MFN anchor frame. It's a really fascinating device. And I guess I should probably take a few minutes to explain it, because it's really cool. I didn't design it, so I can, without bias, tell you that it's really innovative. It's not me bragging. It's someone else's design, a person at Woods Hole Oceanographic that at least one of you know, Don Peters. So this part of it is aluminum tubing that's watertight or airtight, right? So if you put that in the water, it floats, provides buoyancy. Inside of that frame, the inner frame is just a bunch of slats back and forth drilled with holes so you can clamp things to it. And that's where you put all the instruments. That's sort of around the outside of those tubes. In the middle is actually open. That's an open hole, and inside that hole goes this thing, which is an anchor module. And the top part of that is buoyant. This orange foam floats. Inside the hole of that orange foam is synthetic line that's spooled up, wrapped around in there, and stuck together with a little bit of glue. Underneath it is an anchor. That's a cast steel anchor that weighs about 5,000 pounds in water. So you have this whole system together, right, the way it looks on the far right. I'm not going to tell you how you got it in there, but anyway, say it's already in there. And you need to get it back. You come up within range of this, and you fire what we call acoustic releases, right? So we can talk through the water using sound. We tell this release to unhook itself. And what it does is it releases this part, this buoyant part, from this, which has previously been connected to. And the anchor frame here, or the instrument frame, you might call it, floats to the surface. And you can actually recover everything except this little orange module in the anchor without being worried that you're tied to the seafloor because your anchor's been left behind. That's great. You get all the instruments back, you get the buoy back, you take a break, but the anchor's still on the bottom. So you come back to this and you fire another release that's on this piece of equipment. It releases the buoyant piece from the anchor, and this square or oblong piece floats to the surface, but it's still tied to the anchor, right? So what's going to happen? The line inside is going to unspool as this goes to the surface. You're going to be able to clip this, hook this from your boat, pull it on board. You can grab the line that's connected to the anchor, hook it up to your winch, haul back, and pull up the anchor and recover it. So we've deployed with designs like this. The other moorings have a similar but slightly different design. I think I made a rough estimate of the number of deployments we've made at the New England Shelf site, and I came up with about 150 times we've deployed these moorings and recovered them. So out of 150 anchors that we put on the seafloor, we got all 150 back. And that's rare for ocean scientists to be able to do that. So we're kind of moving towards a more eco-friendly approach to this, right? We're not leaving our, it's like pack it in, pack it out when you go hiking. In full disclosure, we didn't get them all back by using this floaty thing. Sometimes we had to go down with an ROV and hook onto it and grab it. But most of the time, it worked. We have a lot of instrumentation out there. Maybe for this audience, I won't go through it in detail, but if you're a researcher, you can just look at that left-hand column, scan through it really quickly, and you can see that on all of our platforms, we have these 5 or so kind of core measurements. And on this coastal surface, here's the quiz. CSM stands for coastal surface mooring. On the coastal surface mooring, which is the one I just described to you, we have all of this stuff, right? We have all the interdisciplinary measurements we can possibly cram in there. That wasn't enough for the people at the Innovations Lab workshops that wanted to move this array to the MAB. They wanted more instruments. In fact, they wanted almost 40 more kinds of instruments or measurement concepts. That was great. It was really good to see that and talk about it. Thankfully, during the workshop, there was a sort of a down selection to about a dozen possibilities. That was still too much for us actually to implement. Remember, our goal, our supposed plan was just to take what we had and move it to the new location. Nobody said anything about putting 120 new instruments out there. So, but we had a little bit of leeway, and we were able to get it down to about 7 different new instruments, which I'll show you on the next slide. We down selected further by thinking about whether they address the science themes, whether that's something you could buy at the store, or whether you had to build it and design it, how feasible it was to operate, and how much it cost. So we got down to these 7. Some of them, thankfully, came from our existing inventory of equipment, so we could just reposition them. We didn't have to buy new ones. Other ones, the ones in red, are part of a procurement process that we're in the middle of right now. And I guess the point here is that if you remember back to that science slide, I said that one of the themes was biogeochemical cycling and the cycling and transports of things like particulates and carbon. We don't have that many measurements. Oh, and the impacts on the ecosystem. We actually don't have that many measurements of those things in our previous instrumentation. So these augment our previous instrumentation with things like turbidity, suspended particulates, phytoplankton, and also extend some of the measurements that are more conventional, like temperature, salinity, and velocity, extend them closer to the surface. So as I said, we're in the process of procuring this, deciding that whether we can afford it, and lots of other stuff. So, but that's the plan. And I think we will do most, if not all of that, will probably be successful. So this is the part that maybe you're most interested in. What is the proposed array design? Here's Nag's Head, which I now know is over there. These circles are the proposed locations for the moorings. There'd be 7 different sites. We put 10 moorings at 7 sites. Why do we need 10? Why 10 moorings at 7 sites? You'll see on the next slide that I talked about them being in pairs, right? So some of those sites have 2 moorings at them. That's the nominal locations. That red box is the same red box I showed you on the other slide with the currents and convergence. So we're right in that realm where it's converging just north of Cape Hatteras. And to extend the region a little further, there's the potential to operate a few gliders out in this bigger glider box. It should be stated clearly that we do not fill these boxes with measurements or instruments of any kind, right? This is just the region within which we can operate. We have actually very few, you can, and these circles are actually huge compared to the size of those buoys, right? So we don't really fill these squares as much as it appears on this figure. So let's zoom in on the red square, see what this moored array might look like. We think of it as a sideways T shape. So there's an east-west line that goes from about 30 meters to 100 meters depth. There's a north-south line right along the 100-meter isobath. And then the extension out into deeper water. So The surface moorings, CSMs, coastal surface moorings, create a triangular array, right? See those 3 orange dots? Basically a triangular array. That array should be coherent. I talked about don't put these so far apart that they're not related to each other. So these are close enough, they should be coherent. And then at each of those locations, you see a second symbol, right? So a triangle, a profiler mooring. So there's the pair, surface mooring profiler, surface and profiler, surface and a slightly different kind of profiler, because the water here is only 30 meters deep, and we can't really use that design that I showed you earlier, so we have to come up with a somewhat different design. Water here, I said, is 100 meters. This is about 600 meters. So that's the proposed concept, is to put out an array that looks something like that, roughly that kind of spacing and orientation. But it has a variety of challenges. There are regulatory challenges. We have to get permitted to do this. There are lots of water space challenges. There are shipping lanes, subsea cables, wind farms, shipwrecks, commercial fishing among the list of things that we have to think about. And in particular, what I've learned fairly recently is that these 2 moorings in particular may be an issue for some of the commercial fishing industry, for the longliners in particular. And so we're thinking about that. We're talking, we hope to talk more about it and try to understand if there's some way we can maybe shift this or distort this array a little bit to make it more compatible with the other water space users. And of course, we could come up with a really great plan, but if it's not logistically feasible and we can't afford it, then we can't do it anyway. What about these gliders? I told you about them, right? So they're moving up and down in the water column, and we're trying to get them to go along a certain track. There are actually glider pilots who work on shore at computer terminals. They can communicate by satellite to these gliders when they come to the surface and give them a new waypoint, a new destination that they will try to fly to. And so overall, in the mean, you can fly them along a predefined track. And what you see here are some of these tracks in different colors. This is that picture I showed you before, right, with the moorings, the T-shaped moored array. And you can see, sort of long story short, the gliders are set up in such a way that they crisscross and go in and around and cross by the moored array over and over and over again. They will go around these lines over and over that 70 to 90-day period. And we have the notion that at least occasionally, once or twice a year, we can go into this bigger box and extend our reach maybe up to Norfolk Canyon and have a glider operate there for a short time and then come down and occupy one of these other lines further to the south. We also have those propeller-driven vehicles, right, that go fast but don't last long. They would do something like this. They're really good at, this is the lines like this, the black lines are what they would do, going east-west and north-south, and that's where we want to see that mural. We want to understand what it looks like if you go east-west and north-south at about 100 meters depth. That's how we'll define that sort of physical system. And finally, or close to the end, I think, operations and logistics. We service the moored array, so those 10 moorings are serviced twice a year in the spring and the fall. And we need to use a pretty big ship for that. We'll probably use one of the largest class of research vessels in the US for that. There's one that operates out of Woods Hole called the Armstrong that we have used many times. The AUVs, we try to get in the water about 6 times a year. Sometimes we don't always make 6 times. And we operate those in what we call campaign mode. I said they only last 24 hours, right? So there's not enough time to really go home and come back and get them. You just stay right out there with your ship. Mike would be happy to do that, I'm sure. Stay overnight, 24 hours, track the vehicle, and pick it up again at the end. The gliders, 70 to 90-day endurance, they are actually the most amenable to a variety of different sizes and types of vessels to either deploy them or recover them. They can be piloted, as I said, remotely, so you don't have to be a glider pilot to put one in or take one out. And we have had success in the New England Shelf Array using commercial fishermen, for example, to help us, sometimes in an emergency situation, sometimes not, but we can call on the commercial fishers to go recover one of these gliders for us or maybe put one in. There are actually 2 moorings in the water right now. At these 2 locations that you see in the yellow circles. We have 1 coastal surface mooring and 1 coastal profiler mooring in the water. They are operating and functioning. They went in in February, and they're doing pretty well. We can monitor some of the information from them remotely, and so you probably can't see the axes on these graphs, but here you see wind speed, and the peaks here are about 30 knots. And this is wave height. The max wave height is in black, and the significant wave height is in yellow or orange. The peak wave heights that were measured here during the same period as those high winds are almost 20 feet. So we've seen some moderately strong conditions out there already during March. These were put in February. Plots here are during March. And the designs seem to be functioning and performing the way we expected them to from the modeling. So far, so good. You all, this is sort of a tease because this data right here you actually can't get so easily. But once we're up and operational, and if you want to look back, for example, at the 6 or 7 years of New England Shelf Pioneer Array data, you can get access to all of it. Anyone can. You don't need a login or an account. You don't have to be part of the university. Internet access, go to that oceanobservatories.org website, start clicking around, and you can find what we call a data explorer. You can point and click and make plots like the ones I just showed you. If you have a little more sophistication, you want to get into having your computer connect to our computer and move things back and forth automatically, you can do that through what they call a machine-to-machine interface. And you can actually even ask real people questions by sending an email to that help desk, and we can help you get access to the data. There's more opportunities than just accessing data, which is the upper bullet here, which I just described. But in fact, it's more likely that the research community will take advantage of these approaches, but it's possible to work with us to modify the sampling, add instrumentation to one of these platforms, potentially add a platform, deploy your own specialized platform within our array, or come out on one of the cruises with us and do some work. So these are all trickier. There's a lot to describe. You can't say exactly how that works until you have a dialogue and a discussion and find out how complex it is, how much time it will take. So this can take a while to figure out, but it's all possible to do. And I think with that, I am at the end of my talk. So thank you very much. Yes?
Hi there. Thank you very much. Such an amazing talk. How long do you think? Oh. Hi there. Thank you very much for the talk. How long do you think the array will be up on the MAB?
Excellent question. Right. I should have said that right at the beginning. So how long will the MAB Pioneer Array be in place? The mantra from the National Science Foundation is 5 to 7 years at a given location. That's about how long we were at New England Shelf. Presumably, if the funding holds up, write your congressman, tell him it's a good array. We'll get 5 to 7 years here, and move to yet another location. Right? There were so many ideas at that workshop that were really neat. Gulf of Alaska, Gulf of Mexico, Puerto Rico, Monterey Canyon in California. There's so many places we could move this and do good science. So, yeah, good question though. There's, more hands up. I guess in the back first.
Hey, folks, just if you would, just wait till we get a mic just so that our online audience can hear your questions. That's why we're doing that. Thank you.
I think this is a multi-part question. These devices, like these moorings, were they designed specifically for arrays like this, or were they designed earlier?
Great question. These designs are specific to the Ocean Observatories Initiative, but they are in fact an evolution of designs that already existed. And so it was kind of fun in a way. Not so much myself, but the engineers involved kind of were able to select the most interesting or the best or the most appropriate bits and pieces of other designs that were in place and converge them all on this. So they're in some ways very new designs, but they're derivative of other designs that were in use already.
As you think about the idea of expanding the functionality, expanding the metrics that you want to be gathering, how do you decide whether it's a new device or it's something you add on to an existing device?
That's an interesting question. I'm not sure I can even repeat it correctly. I'm not sure I understand it correctly. So if we want to make a new type of measurement,
Yeah,
to
I
measure a
think I'm
new
saying, like,
process.
if there's something that you decide that you want to measure that you're not currently measuring,
Yep.
or there's some piece of the picture that's missing, how do you make the calls about this is something we can add on to something we've already made, or we need to create something completely new?
Oh, I see. Yeah, so how do we decide whether we're going to do something totally new or kind of evolve our existing infrastructure to make a new measurement? It's actually, you probably need like a Venn diagram with about 6 different circles, right? So you look at the technology and how ready it is to be used. You look at whether it's commercially available, so whether you can buy it or whether you have to make it. You look at how much it costs. You look at how hard it will be to maintain, even if you can buy it and it's commercially available, but it costs as much to refurbish it as it does to buy it. Like, that'll be a very expensive instrument to maintain. How big is it? You know, can you clamp it on? How much power does it take? So you go through this whole kind of matrix of assessment to decide that our turbidity measurement is an interesting example. We want to try to measure turbidity. We could start with a whole new sensor. We actually are trying very hard, and that test mooring has a side-by-side comparison that we're doing right now. We think we can just recalibrate one of our existing sensors that's a backscatter, optical backscatter sensor to actually provide a turbidity measurement. So that would be really nice, right? So we don't have to bring anything new. So we're constantly evaluating that big confusing structure and trying to make everything work.
Hey, Al,
Yeah, Reed.
that array was out on the New England shelf for 5, 6, maybe 7 years. I wonder if you could speak to some of the engagement with stakeholders along that area beyond just the WHOI scientists and other scientists around the world that are likely using that data, but maybe some of that local community, local stakeholders, and the engagement and involvement with some of those.
Yeah, that's a good point. I can think of two examples right offhand. They're kind of different, but one is the National Weather Service and the ability to do forecasts, both marine forecasts and land weather forecasts. A lot of our land forecasts, as probably many of you know, are actually dependent on observations made in the ocean. So we transmit these data to the National Data Buoy Center, and those data are in turn assimilated into models, predictive models that forecast the weather. So that's one kind of stakeholder. Another group we've worked with is the commercial fishing industry in the area, and that's been a very interesting and kind of delicate balance that we've done, right? We, in some ways, disrupted their fishing grounds, but at the same time, we were able to bring information to them about, for example, seafloor temperature, or the existence of a strong current, or the presence of one of these Gulf Stream rings, which really helped them make their plans, decide whether to leave the dock or not, decide where to go to catch what they wanted to catch. And amazingly enough, the relationship got good enough, and there's other people that have done this much more so than me, some colleagues of mine at WHOI. The relationship got good enough that the fishermen would come to my colleague and say, you know, we just caught this whatever species over here. That's really strange. They're not supposed to be there. We think there's probably one of those Gulf Stream rings you're talking about out there, and we didn't even know it. And so they were the ones that told us. So it can be a really fruitful relationship once you do some negotiation. Yeah.
I'm the commercial fisherman that contacted you about the pelagic longline industry.
Dewey.
And yes, sir.
How are you?
And this off here, good. So I guess we're in the negotiating phase here.
There you go.
What
Yep.
you described with, and hopefully we can have a eventful outcome for both of us. The little frustration in this is the placement of these and the no knowledge prior to about 6 months ago when I received the email from folks in our state about this. And so there was no prior engagement to my knowledge that I know of in community here in Dare County. And also the importance of this area for the pelagic longline industry is there's 15 small home-ported vessels here located in Wanchese that fish these very productive fishing areas. And I'm looking at the buoys here, but I'm also looking at these gliders. and I'm looking at where they're going to be gliding at, both the one that is short-term with its motor and long-term. And it's going right over some areas where I sent you the vessel monitoring system overlays, and I'm curious how it's going to stay away from my gear and other folks' gear. And you know, maybe in the future, as this will be a little bit of constructive criticism, that outreach in the community should have been done first in this decision process of looking at it, and that for that negotiation of the good faith between the industries can go a long way. I think there's some things that can be brought here with meteorology, you know, telling wind speed, wave heights, if that could be published in real time.
Yep.
Where somebody can learn from that, and temperatures and stuff like that could be helpful. But hopefully we can have some further discussion after this. This is a highly productive fishing area, and these two offshore buoys, Plueddemann longline, which is floating surface and lower surface gear, is not conducive to wind turbines or to your two buoys that you have off there. And the U.S. pelagic longline industry is the most regulated environmental conservation in the world, bar none. And hopefully we can continue to fish and provide seafood for U.S. citizens. And you know, the ocean's getting a little more crowded in various things.
Yep.
And we were able to, through some outreach with BOEM, get the Central Atlantic offshore wind area and where our vessel monitoring system overlay was, to get that Central Atlantic offshore area E and F downsized to a smaller area to where we can still fish and live. So that was a good outcome. But I look forward, thank you for your presentation. I look forward to further conversation with you and your colleagues.
Yeah, likewise. Thank you for that. Yeah, agreed. We learned in the New England shelf that we need to, you know, we don't know a lot of the things you're describing, and so we need to learn those and understand how we can compromise. So yeah, let's talk. Absolutely.
I guess I'm having a little bit of a hard time getting a sense of size. What's the diameter of the top part, and what are the dimensions of the bottom part of?
Like of the buoy or the mooring. The mooring's about, the buoy, the foam part of the buoy is about 2.5 meters wide. So you can climb up. You have to stand on a ladder to get to it, and you can walk around on it once you're up there. And the tower is about 3 meters high, so you also need a ladder. If you want to reach one of those instruments and you're standing on the top of the buoy, you need a ladder to get up. So it's kind of that's the size of it. That bottom frame is about 1 meter high and about 3 meters wide by 2 meters wide. So it would fill a big chunk of the front of this room. So I don't know, I hope that helps. They're pretty big. They weigh many thousands of pounds, and we need, it's one of the reasons we need such big specialized ships to do this operation. Just to pick them up off the deck is a fairly big deal. Yeah.
Have you lost any in during the storms? Yeah. Have any torn loose during New England storms at all?
I think it's only happened once. Have we lost any of the moorings or buoys in a storm? It happened once that we know of from a storm, and that was in the Irminger Sea. If you remember that map way back, the first thing I showed, all the different locations around the world's ocean. One in the Irminger Sea, which has some of the worst weather in the world. That one broke free. The others, to the best of our understanding, although we have had a few break, there was some sort of, human intervention of some kind that caused the breakage.
Repeat the question.
They have the microphone so they can, people can hear it, I think, online. Speaking of which, are there questions from the virtual viewers? No, okay. All right, well, I guess we're good. Thank you. Thank you.